Okay, so with an 8-bit timers, we have seen how timer 0 or timer 2 can be configured in TCNT0 or TCCR0 in order to perform the delay calculations and operating the timers. And in the last example, we also seen how the timer 0 can be configured in order to have the largest possible delay, which was 256. Now, if we want to generate a larger delays, because 8-bit timer can go up to 256, we have seen. And if you want to have anything larger than 256, what do we need to do is the question. What we can do is, like we have seen it before, we can create instructions, instruction delay loops, one loop into another loop. That's possible. Or we can use bigger timer counters, like 16-bit timer counters, or we can use prescalers. So as we have already seen the delays in the loops with the instructions, I'm going to talk about a 16-bit counters and also the prescalers now. Okay, so timer 1 and 3, they are 16-bit timers. So we are actually, when we have a 16-bit design, we are increasing the range and also the accuracy of the timers. Timer 1 or timer 3, they have got lots of capabilities. As they are 16-bit timers, the registers are actually split into two because AVR itself is an 8-bit processor. So the largest register that we can have is an 8-bit. So we have to actually have two 8-bit registers in order to use a 16-bit timers. So in this case, we have got TCCR or OCR or TCNT registers split it into two. So for example, TCNT1 is actually divided into TCNT1 low and TCNT1 high. Okay, so two separate 8-bit registers needs to be used in order to implement or in order to use 16-bit timers. So these are also allocated in the special function registers in the I/O registers. And the low byte or the high byte has to be specified in order to use timer ones. And we also have two control registers like TCCR1 A and which is for timer counter 1 control register, TCCR1B. Okay, so two separate control registers that we need to configure based on the operation. And we also have, if we are using in normal mode, we have got timer overflow 1 flag. So when the overflow occurs, that flag goes high. And we also have OCR registers. So it's going to be OCR1A high, OCR1B high, A low, because there are two separate ones that we can use. And based on that, we have also got the flag OCF1A, which can be used with the CTC mode. And the timer 1, the 16-bit timers, they also have got these prescaler options, 1 to 1, 1 to 8, 1 to 64, 1 to 256, or 1 to 24. So we have got these prescalers as well that we can use with the timers. So this is the architecture of it. 3 independent output compare units. So 9 OCRs, output compare register, double buffered, 1 input capture unit, ICR, which is over here, and CTC is still available for auto reloads, 10 independent interrupt sources, which we are going to discuss later, and it also offers rich PWM features. So let's see a simpler structure of the timer 1 and 3. So we have got 3 TCCR control registers, A, B, C. Okay, this can be TCCR1A, TCCR1B, and TCCR1C, or 3A, 3B, and 3C. And same applies for OCRs. So we have got A, B, and C, and we have got TCNT1H and TCNT1L, high byte and the low byte, also 3H and 3L. Okay, so this is the structure of it. And timer interrupts, you can find the TIFR register, OCF 1A, 1B, and timer overflow. And you can also find in the extended timer interrupt flags, timer 3, OCF 3A, 3B, and 3C, and also timer overflow 3. So we can use these in order to have timer 1 or timer 3 for the largest delays and calculations with the largest delays. And read-write operations. Now this is important because as we have slitted the registers into 2, we have to be really careful because all 16-bit registers require 2 read or write operations through the 8-bit data bus. So we have to read or write the low byte and then the high byte and so on. Now temporary register, which we use in between of these 16-bit registers in a 16-bit timer for double buffered operation. This is important. And direct read or write operations from the low byte of the timer registers triggers the transfer between temporary register and the high byte in the same clock cycle. So what it does is, when we want to write a value into the TCNT 1, L and TCNT1H, first we have to load it into H and then L, okay, when we are writing it. And when we are reading it, we must read the low byte first and then the high byte because it's stored in the temporal register. So why we are doing this? It's because we want to prevent timing mismatches between the low byte and the high byte. Okay, we have to make sure that they are stored at the same time in the registers. And OCRNs, they do not use temporary registers. Only TCNTs are using temporary registers. So important part, proper 16-bit write, high byte must be written before the low byte. Proper 16-bit read, low byte must be read before the high byte. Okay, so example is given over here, as you can see. So set TCNTN to 01FF, then load 01 into R17FF to R16. Then, as you can see, the high byte must be written first, so 01 is written, and then the low byte is written, 16 to TCNTN-L. So when we want to read, we read the low byte first, TCNTL into R16, and then the high byte. And the same thing can be done with the C compiler. So TCNTN01XX, and then read it with I is equals TCNTN, and so on. So temporary register for double buffered operation can be demonstrated with this figure as well. So when we do LDI R17 hex 01, this is the data bus, okay? And what it does is, as we are writing to 01 to our TCNT1H, so from here, you can see that data bus can directly access to TCNT1L, okay? So this one has to go into the temporary register and then TCNT1H. That's why we first need to write over here, and then from there to there and there to there, they can have written at the same time. That's why we had to write that one first, and the next clock, these are two stored in the same register. And same applies for the OCR 1H, and L is directly connected to data bus. So this makes sure that we load them at the same time. Because our data bus is 8-bit, we can load the both registers at the same time. That's why we had to load high byte first into the temporary, and then that will be in the second clock. When we have got a new data in the data bus, that will be stored here, and the value that is in the temp will be stored here. Same applies for the OCR one as well. And when we want to read it, so reading back again, so we read the low byte first, okay? And then we read the high byte, because what it does is the low byte is read it first, and this one goes to the temp again and to the data bus. So we just need to be careful when we are reading and writing it, and each of the registers accessed individually, and in 16-bit timers, we should read or write the entire content of the register at once. This is important, okay? We have to do that at once. So the modes for the timer is given, and normal modes and the CTC modes are the ones that we use generally. PWMs, we are going to see that in a different chapter. CTC modes, you can see that they have a different options, but they are just actually performing the similar operations. So this is for input capture, this is for OCR, so we can generally use for CTC 0100 and the normal mode as 000. And we have to configure TCCR1A and TCCR1B in order to do that. We also got the prescalers. We also got some other configurations that we can do with TCCR registers. And another important part of the timer counters are the output compare unit. So if you want to have output compare unit for waveform generation, okay, so we have got a 16-bit comparator over here, and we have to use the OCRN 16-bit registers, OCRN H and L, in order to do that. And the TCNT values are loaded. Then when it matches the OCRN in the 16-bit comparator, we can activate the waveform generation, and we can actually use the output compare unit. So from the COM, from the TCCR, as you can see, we have got some COM operation pins, normal port operation. So 01 is a toggle on OCN pin, and 10 it's clearing, and 11 is setting those pins. So set to 0, set to 1, and toggle 0 to 1, 1 to 0. They're both acceptable. So here is an example. Let's talk about the timer 1. Now, what do we have? We have got a 10 megahertz clock timer 1 to write a program that toggles PB1. So it's a similar example that we have done with the timer 0. Now we have to use timer 1, and the period is 1 per millisecond. Okay, so let's start again with analyzing. So 10 megahertz will give us 0.1 microsecond. So number of machine cycles, what do we have? 1 millisecond divided by 0.1 microsecond. This will give us 10,000 number of machine cycles. Now, 10,000 is not something that we can handle with 8-bit timer. And 16-bit timer, we know that is 65,536. So we can set the TCNT1 to be 65,536 minus 10,000. Okay, so this is going to be 55,536. Or if you want, you can write this in hex as D8F0. So the high byte, the low byte. Okay, so we can use these in order to configure TCNT1H and TCNT1L. And we know that we have to write H first and then L into the addresses. So we have got most of the information required, and then we have to configure TCCR1A and TCCR1B, and we have to look at the IFR register. So we have done that calculation, TCNT1 loaded with D8F0, TCCR1A, it's in the normal mode, so I don't need to set anything. So if you want, you can ignore it, or you can just say 0 hex 00. TCCR1B, no prescaling, none of the modes are selected, it's in the normal mode, so 0 hex 01, and we have to monitor TOV1. Monitor TOV1 flag. Okay, so let's write the code for it. Once again, dot include M128 def.inc. So let's use delay 1 millisecond as a subroutine. So in order to do that, if I want to implement a subroutine, I have to use a stack pointer LDI R16 high Ramen, and then out SPH R16 LDI R16 low Ramen, and then out SPL R16. So these are all defined, and as we are going to use PB5 again, toggling SPI DDRB5 set bit. So PB5 as an output. Let's say init stack. So what I can do is SPI port B5. So I can say PB5 is equals 1. And I can call the delay 1 millisecond, which I'm going to implement. And then toggle it. So CBI port B5, and that will be PB5 0. Okay, so we have to toggle it 1 millisecond delay in between, and I have to call delay again 1 millisecond and R jump, go back and start again. So we have to start from here. Okay, so this is the main. Now, outside of the main, I have to use delay 1 millisecond subroutine. And I can say for the timer TCNT that has to be initialized. So LDI R20, I can use low, or let's say we have to load high first. So high D8 F0, okay. So 0 hex D8 F0, and then out TCNT-H, TCNT1H R20, and LDI R20 low 0 hex D8F0, and out TCNT1L R20. So these are what we have got it over. If you want, you can write these as minus 10,000. This is also acceptable. The compiler can understand from that as well. So afterwards, I can reset. So I can have TCCR1A to be 0. So R20 will be 0, and out TCCR1A to be R20. Okay, so and LDI R20, this should be 1, 0 hex 01. Out TCCR1B to be R20. So the normal mode, no pre-scaling, nothing. So we have set the timer configurations and set high byte. I just want to write set low byte of the timer. Then over here, normal mode, no pre-scaling. Okay, done. So we are ready now. So what we need to do is we have to monitor TOV1 flag. So again, in R20 TIFR register, let's load it into the R20. So read TIFR and then check if it is set. So R20 TOV1 flag. And if TOV1 is set, skip next. Then rjump again. So I have to monitor it until that is set. So I can say again over here. So once that is done, if it is set, that means I have to clear the flag LDI R20 1 TOV1 and out TIFR R20, clear TOV1 flag. Afterwards, stop the timer LDI R19 0, out TCCR 1B to be R19, stop timer, and out TCCR 1A to be R19. That will be also for stop timer. And then we can just use return. So when it is done, it will go back to the main function and toggle port B. So this is how we can implement using timer 1. And if we want, we can also do this as I already mentioned, rather than using that, you can use minus 10,000, which we already get it from the calculations. In CTC mode, all we need to change is 10,000 minus 1 because we have to set the OCR. Okay, so 0 to 9,999, which is 270F. And we have to load these into OCR1AH and OCR1L. And as this is in CTC mode, this pin has to be set in the TCCR1B. So we just need to modify this code, and this part is remaining as it is. So the timer part we have to configure. So TCNTs, maybe I can just put this down. Let's copy this. Oops. And let's have it over here. So let's say CTC mode. So I will make the modifications over here, then I can get rid of that because we are not going to set anything in the TCNT, so they are going to be 0 hex 0 0. So I can say temp is equals 0, and over here TCN T1 L equals 0 and TC and T1H equals temp. Okay, so then I have to load OCR1A and OCR1H. So we have to make a modification here. LDI R20, it's going to be 27, 0 hex 27 for the high byte. Out OCR1 AH, it's going to be R20, and LDI R20 0 hex 0F, and that will be out OCR1 AL, and that will be R20. So here, once again, temp is 0 hex 27, and here it's going to be OCR1AL to be 0 hex 0F, and OCR1AH equals 0 hex temp in this case because it's already stored in temp. So OCR registers are set, which we need to match and compare. Then rather than having it in the normal mode, TCCR1A is still 0, and this is going to be 9. So that has to be changed to 9, and this will be in CTC mode. I'll just say CTC mode. So we have set that to 9. And TIFR OCF1A will be monitored. So we have to modify those. Is set, then clear. So OCF1A has to be cleared. And we have to stop the timer. So CTC mode, everything is related with the OCR and OCF, so we have to find the OCR value, which is 0 to 9999. we have to set those values. TCNTs has to be 0, which is counting up from that point to 0.9999. And TCCR has to be configured so that it can be in CTC mode, and we have to monitor OCF1A flag. Okay, so that's the code in CTC mode that we already written over here as well. Now the prescalers. So larger delays can be generated from the bigger counters or from the prescalers. So the size of the time delay depends on the crystal frequency and the timer's register. Now, prescalers can be used to increase the delay by reducing the period. So we are actually doing a clock dividing. And we can reduce the period, 8, 64, 256, 124. We can make these modifications. And in the 16-bit timers like timer 1 and 2, 3, we have got these clock sources, CS1, 2, 1, 1, and 1, 0, or 3, 2, 3, 1, and 3 zeros, which you can use these prescalers, or you can use also external clock source pins as well in the timer 1, 0. So timer 1, 2, and 3, they are sharing the clock resources. Only timer 0 does not have any external clock. And they are just using the similar prescalers, as you can see from the clock select. And each of them has their own outputs with the 10-bit prescalers, so 8, 64, 256, and 124, in order to have clock division based on the delay that we are required. And we'll do an example to see how we can do these calculations in order to select the prescalers that we are looking for. So here is the example. We have got an 8 megahertz clock, write a program to generate 1 hertz frequency on PC4 pin. 1 hertz corresponds to 1 second. So that's going to give you a 0.1, 0.5 seconds high and 0.5 seconds low. So 8 megahertz. We have got 0.125 microseconds is the period. So 1 hertz is giving us 1 second, and when we consider it, 0.5 is low, 0.5 is high. Okay, when we think about it as a second wise. So how do we calculate and how can we generate using prescaler? It's important because we cannot generate that using a ordinary 8 megahertz clock, which is going to give us 0.125. So 0.5 seconds divided by 125, 0.925 is 4 million. We cannot handle that with a any of the timers. And if we think about a prescale 8, this will give us 1 microsecond, 0.5 divided by 1 microsecond, 500K, still too large. We cannot handle with any of the timers that we have got. 64, 0.5 divided by 8 microseconds is the 64. If we do a prescaling of 64, we'll have 125 kilohertz, which will give us 8 microseconds. This will be 62.500, which can be handled. 256 giving us 31.25 kilohertz, which is 32 microseconds, which is 15.625, 15,625. And 124 is giving us 7.8 kilohertz frequency and 128 microseconds, and that is giving us 3,906.25. Now, these two are too large. This one is not an integer, so we just have two alternatives, either 64 or 256. 64 looks like easier to deal with it. It's 62,500 is the value that we are looking for, that we need to load into TCNT1 register. So that means 0.5 divided by 8 times 10 to the power minus 6, which will give us 62,500. Now, 62,500, if you are using timer overflow normal mode, that means we need to have 65,536 minus 62,500 normal mode. Okay, or if you are using, let's say, CTC mode, this is going to be 0 to 61,499, or you can write this as 62,500 minus 1. So you don't need to do a calculation over there. Okay, so that's how you can use it, or if you want, you can convert it to hex. But compiler is doing that for you, so you don't need to worry about it. You can just directly write them in the decimal value, and compiler will convert it for you. So the code is similar again. We are using initialization of the stack. At this point, we have to use port C, pin 4. Okay, so then we can call delay 1 second, and 62,500 minus 1 can be used. OCR1A and OCR1L has to be configured, and these are loaded into the OCR1H and OCR1L, F423. TCNTs, they are 0, as we are going to start counting from 0 to this value. TCCR1B, we are using here 1B, and it has to be configured so that it's in CTC mode, and we have got a Prescaler 64. So if I go back, so Prescaler 64 is 011 in TCCR 1B. That's why this is configured as B, 1011. And we have to monitor the OCF1A flag. It's the similar thing. When it is set, we clear the flag, we stop the timer. If it is not set, we keep monitoring until it is set. So the modifications are generally done with the OCR based on the delay that we want. And depending on the mode, either we set TCNT or we set the OCR values in there. And another important thing that we can do with the timers are counting events. So that assuming that the clock pulses are fed into the T1 pin, write a program for counter 1 in CTC mode to make port C high every 100 pulses. So what do we mean by this? Again, we need to look at the configuration. So T1 pin on timer 1, okay, so external clock source pin. Either we are looking at the rising edge or the falling edge. We have to decide on that. We can choose falling edge in this case, in this example. TCCR1A is still 0. The mode is CTC mode, so that's why it is 0, 1. And the clock source is external clock source on the falling edge, which is 1, 1, 0. So this is going to be configured as 1, 1, 1, 0, which is E. Okay, so we can say TCCR1A equals 0, TCCR1B equals 0 hex E. That's the important part of it. Now, it is telling us that it has to be 100 pulses and in CTC mode. 100 pulses means 100 minus 1, 99 pulses, because we start from 0 to 99. That will be the count. So we have to load OCR 1AH and OCR1AL based on that to 99. But the 99, we know that this is going to be 0 hex 0, 0, and this is going to be 0 hex 99. That can be fit. So that will be loaded. And then TCNTs, we don't need anything over there. So we just need to monitor the TIFR if there's a match. And if there's a match, we just do the operation. So we have to make TD1, so T1 to be an input, which is in AVRP port D6 pin. So in order to make it input, we just clear port D pin 6 to be 0. And as we are going to set port C pin 0 to be high, we have to make that output port. Then TCCR A will be 0 and TCCR1B will be hex E. So those are configured. CTC counter on the falling edge. That's accepted. And then what we do is we load the 99 into our OCR registers, because this is the point there which we have to compare and set and check the flags. So OCF1A flag is if it is set, then if it is not, we keep doing it. If it is set, we clear the flag. And then what we do is port C, it's going to be 1. So we toggle the port C by setting and clearing the port C. And we just do this again and again. Okay, so we can actually use or modify the timer to count an event based on CTC mode. Whenever the pin receives a new value, it will just compares it and sets the port C. So timer 1 and 3 input capture unit. When an event occurs, the value of TCNT is captured in ICRN. So ICP pin is here, so TCCR1 or TCCR3B is configured. So ICNC is the input capture noise canceller. It's a digital filter that requires 4 successive equal values for triggering, and ICSN is a triggering edge, 0 falling edge, and 1 rising edge. So we can monitor that and we can configure it according to our needs. So analog comparators can trigger TCNT1 but not TCNT3 register. And a simple C code for sequencing regular actions. So the counter timers are often most valuable resources at your disposal. Creation of multiple repeated timed events for one timer. You can use these simple C code for sequencing regular actions. And if timer ticks this, do every 8 ticks, do every 16 ticks, and that can be used. And output compare modulator. So generating PWM signals, which we are going to see later on, They can be used with the chip modulator to generate waveforms for modulated with frequency carrier frequency. So timer 1 or timer 2 can be used, and we can generate the waveform from the pin OC1C or OC2. Okay, so we are going to talk about more about the waveform generation in another chapter. That's all I want to say for today. Thank you.